Okay, so the purpose of this little mini lecture is to give an overview of what is Bayesian statistics and just give some of the basic intuition and definitions, so that we can all understand what the Bayesian paradigm of thinking about uncertainty entails. So just to start off with a very simple example. Imagine you've picked up a coin and you don't know like how often it'll come up heads or tails, and so that's one very simple but yet understandable way of just talking about what probability is, right? So if you do an experiment, which is to flip the coin, then you will start observing outcomes, and that's what, in the statistical sense, for our purposes, is what we will call data. And so, not to belabor the difference between Bayesian and frequentist thinking, but one kind of hallmark about Bayesian statistics is that we encode what we know or what we believe about unknown quantities, so quantities that we're not certain about. We encode them using probability distributions. And so, coming back to our coin examples, suppose you pick up a random coin. You might believe, because you've seen coins like it, that even without flipping it, you would expect somewhere around a 50% probability, say 50% chance to come up heads or tails. And so what a Bayesian would do in the analysis would be to encode that information in what we call a prior distribution. So you would put a probability distribution on what the probability of heads is. Okay, so let's give a little bit of notation. So you can imagine there's some quantities, and we need to be able to express them. So let's talk about the different quantities. Okay, so let's use the coin to motivate this notation. So suppose we're going to flip it, planning to flip it some number of times, let's say n times. And so each time you flip it, we'll record one observation. So let's call these, let's use the letter y, just like in the book, just for consistency. So we'll record the outcomes y1, y2, up to yn. Okay, so those would be our coin flips. And so we can just record each of them as, say, like 1 or 0. Now, so this is going to be what we call the data, because this is what we're going to observe from the experiment. And so now, of course, what you get out of this data is very much related to what we're going to call the unknown, what we can call the unknown model parameters. So that's what I was alluding to when I was introducing the concept of prior. So in this example, there's really just one key parameter we care about. So I think the general notation we'll use for model parameters is theta. So let's put theta here as our parameter. Okay, so it's a model parameter. And so for flipping coins, then this would simply be the probability of heads. Okay, just to continue that example. That's our model parameter. And so while we're talking about quantities, there's also what we can call explanatory variables. Okay, so you may have seen that in the first chapter. And so suppose corresponding to the data, we have some other known constants that could help us explain the data. So x could be like, for example, who flipped it, for instance. And we thought that was like one sort of predictor for what the outcome of the data would be. Okay, so I think these are the main quantities we want to list out for now. Okay, so what's distinctive about Bayesian statistics is what we consider to be fixed and what we consider to be random. Okay, so let's go over here. So these are called explanatory variables, or we can also call them covariates. Okay, so from the point of view of probability, then we treat these covariates as what we call constants. So we don't put these are quantities that we do not put a probability distribution on. So these are constants. And in contrast, everything that has uncertainty associated with that we don't have certain knowledge about, we can put a probability distribution. So in this case, it would be all of the data. Okay, so all the data are considered random, and then the model parameters, since we don't know what it is, and in this example we try to estimate it. So we treat all of these things as random variables. Okay, so these are random variables. In that they have a probability distribution assigned to them. Okay, so with that said, then we can start writing down a few the key expressions for probability distributions that underlie Bayesian inference. Okay, so first, we need to explain where this term Bayesian comes from. And so Bayesian is named after Reverend Thomas Bayes, who was well known for developing what we now call Bayes' theorem or Bayes' rule. Okay, so this, I won't assume you remember it, so let's just write that down. So kind of underlying this whole subject is this probability relationship, which is known as Bayes' rule. Okay, so here, so A and B are events in the probability sense. So in other words, it makes sense to talk about what's the probability of A happening, what's the probability of B happening. Okay, what's the probability that it thunderstormed? Will thunderstorm tonight in Waterloo? There was a big thunderstorm, by the way, last night. So what's the probability that, say, it will thunderstorm in Waterloo tonight, given that, say, it thunderstormed last night? Okay, so you can think of these as any two events in a probability sense that could be related to each other or not. Okay, if A and B, so that's where we get into the notion of statistical independence. Right? Is when two events, you can simply, if they're independent, then you can simply multiply the probability that they both occur by simply multiplying the probability that A occurs times probability B occurs. Okay, but in general, there could be some relationship, and in that sense, it would be useful to look at the conditional probability of one given the other. Okay, so we can look at, so in probability notations, we use big P for to denote the probability. So this is the notation that's useful to start getting familiar with. So how you read this is a probability. Okay, so probability is a function that's evaluated on events and outputs a number. Okay, a probability between 0 and 1. Okay, so here in this case we're talking about a conditional probability. So the input is two events. Okay, so this bar. Okay, you read it as given. Okay, so this is the probability of that A happens given B has happened. Okay, so we treat B as known and having already happened. Okay, so that's the conditional probability. Okay, so in my example, if it's more likely to thunderstorm, given that it thunders today, given it thunderstormed yesterday, then this would be bigger than P of A, right? If I didn't have the information about the fact that it thunderstormed. Okay, so that's how we encode these kinds of relationships in using probability, the rules of probability. Okay, so how can you express this? So the famous formula starts with simply rewriting this conditional probability using the definition. So conditional probability means that A given B, so you calculate the probability that A and B both happen. Okay, so that's the intersect symbol. So that's the cap. So A and B both happen, and then divide by the probability that B happen. Okay, so by definition, that's how we calculate this conditional. And now you realize that you can write this a different way, and it's simply realizing that P of A and B, so this intersection, can be written as conditional A given B times P of B, but you can also switch the roles of A and B. Right? So this formula would also be valid if I did B given A and then P of A on the bottom. Okay, so if I do that, then I have two ways of writing P of A and B. Okay, so that's where we get the second half of this formula from, is simply to take the other way of writing it. So here, this intersection is P of B times A given B. Okay, so the other way to write it would be P of B given A, P of A. Okay, and so that's the famous formula known as Bayes' rule. Okay, so the thing worth pointing out here is that A given B and B given A are very different quantities. Okay, and they can be very different. There's a lot of applications where this can be misinterpreted. Okay, so imagine you're a judge and you're trying to determine whether someone's actually guilty. Okay, so then you want to, well, you can imagine you want to calculate the probability that the person on trial is guilty given some evidence. Okay, and you want to get that right rather than calculate the probability that you have seen the evidence given that they're guilty. Okay, you can imagine that can be those can be very different, but they're related. Okay, so innocence given the evidence is related to evidence given innocence, and the way they're related is to actually multiply the ratio of what we call the two marginal probabilities. Okay, so I think that's good enough for intuition for now. Okay, so that's Bayes' rule applied to events in general, but we can do the same thing in probability when it comes to probability distributions on random variables. Okay, so let's look at the relationships between. So we're going to focus primarily on the data and the parameters because constants you don't put probability distributions on. So, but we're just pointing it out here because sometimes there are useful things we measure about, for example, about our subjects that we can include in the model as predictors, but we may not need to model them explicitly. Okay, so so you can think about there could be many examples of covariates when we later when we do our modeling. Okay. Okay, so we're going to focus on this. So because these are all random variables, so therefore they have a joint distribution. Great. So let's say, the random variables, I'm going to abbreviate them as RVs, so they have a joint. So I should list them. So the random variables, which we do want to model, are all the y's and theta. So they have a joint probability distribution. Okay, so we're going to denote that as P y1 up to yn and theta. Okay, so just for notational simplicity, I'm just going to write y for all the for a list of data, just for notational simplicity. Although I will make let's make a little bit of a comment about what's known as exchangeability. Okay, so what's called exchangeability in statistics is that you can change the labels of these y's, and it's the same, and it's going to be the same probability density when you plug it in. The most often used and classic example of exchangeability, which is stronger than, but often is used in modeling, is what we call IID. Okay, IID stands for independent and identically distributed. So a good example of that. I mean, it's an assumption that often you cannot perfectly test, but our coin flip example comes pretty close to that because it's saying the outcome of all the coin flips is independent. It doesn't matter what order I label the y's. They all have the same they all have the same probability distribution y given theta. Okay, so that's a common modeling simplification that's used in practice. Okay, so in that case, then all you need is just one probability density of y given theta. Okay, but I'm getting a little ahead of myself, so let's start with what we have here. So let's call this. So this is the joint distribution of the data and the parameters. So y. I'm just going to use the simpler form. So y and theta. Okay. So you can write this in two ways. Again, according to Bayes' rule. Okay. So that's why all this has now been called Bayesian inference, because Bayes' rule underlies all these manipulations. Okay, so this is the basic formula that we'll be applying many times. Okay, so I have you can think of y and theta now. So this is a density, so they're not strictly events, but you can apply this this notion to them. Okay, so you have y and theta together. So this is like the intersection of a and b. Right, so we can write that in two ways. Okay, so we can write it in the first form, y given theta times probability theta. Okay, or equivalently, we can also write it as, so we can also do it the other way. So we can also write it as theta given y, p of y. Okay, so that's just applying what we have over here. Okay, so that's key to developing what we're soon going to define as the posterior distribution. Okay, so some of these things have names. Okay, so let's name them now. Okay, so there's four probability densities here, and they all have names. Okay, so let's label them so we have them for reference. Okay, so this guy. Okay, so theta given y. Okay, I'll explain why they call these later, but let's name them first. So that's the posterior. Okay, and then we have p of y here. That's called the marginal. And then these two terms. Okay, so this guy p theta is the prior, and then this guy y given theta is the likelihood. Okay, so I'm going to explain all of that. Let me just give myself a little more room. Okay, so now my motivating example, you can see comes into play here now, because we have p of theta, right? So going back to our coin flip, so you might assign a probability distribution to theta, where most of the mass is around 0.5, for instance. If you believe once you pick up the coin that it's most likely a fair coin. Okay, so that you would encode that belief in this probability distribution p of theta. Okay, and so philosophically, like we can. The Bayesian paradigm is quite intuitive, because it says, okay, so you start with some belief about this unknown quantity, and as you start to see more and more data that involves that unknown quantity, we learn more about it, and therefore we can update what we know or what we believe about that quantity. Okay, so that's the intuition behind the Bayesian way of thinking about learning unknown parameter.
Can I ask a quick question?
Yeah, for sure.
So just the name make a branch, because prior, basically, because you distinguish what's a beta random variable and model parameter. So the one p of theta is the one associated with beta. That's what you call prior, because it's distinguished as a model parameter. Yes. P of y is called marginal because the y is beta associated.
Yeah, exactly. Yeah. So yeah, exactly. So y and theta are not exchangeable. Okay, just to apply that concept.
Okay, so
yes.
It's just because there's a distinguished category there. Okay.
Yeah. Because we have defined y to be the data, and then data we're assuming implicitly comes from a probability model, and the model has some parameters which are called theta. Okay, so that's good. Yeah.
Okay.
Oh, and that actually might as well add. So in this case, we're assuming we might have some covariates, but we're not going to model them, right? But if we wanted to, we could, right? So you could imagine modeling like y given x, and then x given theta, and then theta given phi, and that can go on, right? And that's allowed in the Bayesian framework. And I think when we go into the application of what we'll be tackling together, I think we will see layers like that. And so chapter 1 calls that model hierarchy or hierarchical models. Okay, so that's certainly allowed. For now, let's just keep it at one level, so it's just easy to understand. So y is data, and theta is the prime. Okay, so so the other key thing here is the posterior. Okay, so the reason we have all this labeled is because ultimately we want to learn about the unknown parameter. Okay, we're gonna see some observations. Okay, so we're gonna see some realizations of the random variables y, and based on those realizations, we want to learn about theta. And in essence, we're updating our belief about theta. Before we flipped any coins, we believe it follows this probability distribution, but let's say we flipped it n times. So the posterior, okay, it's labeled here as the posterior, is the distribution that captures what we believe about theta after we see the data. Okay, so therefore it reads very cleanly here, right? Probability of theta given y. Okay, so probability of what we believe about the parameter given the data. Okay, so that's the key to all of Bayesian statistics, is how we go from going from a prior to a posterior, and then using the posterior to draw conclusions about the parameter theta. Okay, so in a nutshell, that's what we're doing. Okay, so now let's actually write down that expression. So the key to Bayesian inference is okay. So the basis of inference. Okay, is the posterior. Okay, so I'm going to write it again. So theta given y. So what do we know about the parameter after we see the data? So this is the posterior. Okay, so it's this guy. So it's posterior. Okay, so if I rearrange this formula, okay, so I can rewrite the posterior as okay. So I'm gonna use these two equalities to basically just rearranging. So the posterior is going to be equal to the likelihood times the prior divided by the marginal. Okay, so according to this expression. Okay, so this is it is a probability distribution. Okay, so in other words, what do we know about probability distribution is if it's continuous, then we know the integral of the posterior would be 1. Okay, so that's or if you're talking about more simply in a discrete case, if you add up all the probabilities, all the possible outcomes, all the probabilities add up to 1. Okay, so that's the same idea. Okay, so this is a probability distribution about the unknown parameter. Now, because we know that this posterior is, let's say, has to integrate to 1, okay, so we treat this, okay, so you can read it as probability of theta given y, okay, so in this distribution, we can treat the y's as constants, because they were data, we observed them, we have now plugged them in, and we now have a probability distribution in terms of theta, okay, so this is important. Remember, this is a function, the probability is a function of theta, okay, and so therefore, anything that involves y, for our purposes, is simply a constant. Okay, so it's common practice. So you see in the denominator, there's a term involving just y. So we can treat this p of y simply as a constant of proportionality. Okay, so that's why we see this is a common thing to do in terms of getting the form of the posterior distribution, or in other words, getting the posterior distribution up to a multiplicative constant is all that's needed. Because if we want to, at least in theory, if we want to then get the proper probability distribution, we just need to find the normalizing constant, okay? And I make it sound very easy, but sometimes this is extremely difficult depending on what kind of problem is being tackled. Okay, but for conceptual purposes, we know everything we need to know about this distribution by just knowing the numerator. That's the point I'm getting at here. Okay, so this is, you can read this as proportional to. Okay, so this is proportional to the likelihood times prior. Okay, so in other words, this is kind of like the Bayesian mantra, is you say the posterior. How do you get it? You take the prior, okay, so you take the prior, and then you multiply it by what we call the likelihood. Okay, so that's the basis of inference. Okay, so let's develop that. So I think based on that we can expand on that coin flip example and make it a little bit more concrete. Okay, so let's keep things fairly simple. Okay, so can I get one of you to participate by, okay, so give me, let's say you found a rusty old coin. Okay, so give me a reasonable prior for theta, just for this illustration. Okay, what do you think? Okay, if you just found a random coin, what would you think the probability of heads would lie between if I didn't tell you any other information? Okay, who's gonna give me this is an easy question. You can answer easy one first.
Just a half to get things moving.
Okay, you should give me a range. Unless, see, so this is actually crucial, right? Because unless you know for sure, if you know for sure it's a half without seeing any data, then you don't need to do any of this, right? So that's kind of the point we're getting at here. So maybe you would think it's in some okay. Oh, I'll do it so I can illustrate my so I can illustrate my point. So let's say you have, so we know this guy, so would lie between 0 and 1. So you probably think it's pretty close to half, unless you have reason to believe otherwise. Okay, so how would you? So what I'm getting is, how would you encode this as a probability distribution? So this probability is continuous, so we would draw some sort of curve. So depending on how sure you are that it's close to 0.5, we might draw something like this, right, to encode our belief that in fact the probability of heads is pretty close to 0.5. Now, if you were even more sure, then you know what to do. You just make this sharper, right? And so we can come up with certain parametric probability distributions that can capture the shape of a probability density. Okay. Whereas if you weren't sure, weren't that sure, then this gets at another key point about Bayesian statistics, is that it's there can inherently be some subjectivity, right? So my prior might be different from Andy's prior, right? And that might be different from Eleanor's prior, okay? And so there is, of course, a whole lot of literature about how you select priors, but we're not going to get into that today, other than to say that you should, in practice, design it to encode what you know or don't know about that parameter. Okay, so someone might give me this black prior, and then someone who's even more sure might have a prior that looks like this, and yet another one of us might have a more gentle prior, right? So all those are valid priors. Key thing is they encode what you believe about the parameter. Okay, so what is P of theta? Well, simply these curves will encode it as in most cases a parameterized probability distribution. Okay, now the likelihood part. Okay, I think this is slightly more straightforward, and that's what's called the likelihood principle. Is well, if you assume a particular model, then the likelihood gives you independently of your prior, right? The likelihood gives you the probability of observing the data you did. Okay, so suppose we flip the coin twice. Okay, so let's do the experiment. Okay, so let's flip the coin 2 times. Okay, and so in this example, we can actually explicitly write down what this term is. Okay, so this is really just talking about the probability distribution of y given theta. Okay, and then we're going to assume the flips are independent, which I think is reasonable. Assume independence. And so so what are the possible outcomes then for y is, well, let's count y to be number of heads, so you have 0, 1, and 2. Okay, so let's make a little table here. Okay, so this is the value of y. Okay, so 3 possibilities are 0, 1, and 2. And then this is the probability. I should. Okay, so let me fix that because I'm talking about the probability has to be. This is the model-based probability. So this is conditional on what we're assuming from the model. I mean, in fact, there's really only one plausible model for this situation, and some of you probably heard of the binomial distribution. Okay, since we're counting the number of heads, right? So it's independent trials, and then we're counting number of successes, in this case heads. Okay, and the probability, of course, says that it depends on this parameter which we don't know, right? If we knew it was, then we can just plug it in, okay? But first, let's just write it in general. Given that, let's say theta here is the probability of success, or probability of heads, okay? So using elementary, I think many of us learned how to calculate this, I don't know, sometime in grade school, right? If you have a probability theta for heads and they're independent, you can simply multiply theta times theta. So we have here theta squared. Then probability of tails would be 1 minus theta, and then if you do it 2 times in a row, then you multiply those two, so you get 1 minus theta squared. Okay, and then what's this one? Well, there's 2 ways to think about it. You can just say, okay, well, they have to add up to 1, so I just take 1 minus these 2, or we can just calculate explicitly. I mean, it doesn't matter which. In this case, it's simple enough. So you get let's say, heads and then tails, so it would be theta times 1 minus theta, or you could get tails and then heads, so that's 1 minus theta times theta. So either way, you add it up, it's 2 of theta 1 minus theta. Okay. And so, for example, you can plug in some numbers and you can verify that this is actually sane. Okay, so you say theta is 0.5, then you quickly see, okay, there's 0.25, right? 0.25 probably you get 2 tails, 1/4 chance you get 2 heads, and then you have 50%, then you get 1 head and 1 tail. Okay, so this is a simple illustration of what we mean by the likelihood, right? In this case, you can explicitly see the likelihood is the probability of observing this particular data given the value of the model parameter. Okay, so now you can kind of see how this works, because once you observe the data, suppose we got two heads, then we now know that our posterior would simply be theta squared times whatever we decided to use for the prior, and you can see immediately that the only unknowns left in the posterior is theta, right? You can see it's clearly a function of theta. Okay, so that's how we get a posterior. How are we doing for time? Maybe another 5 minutes, and then I'll wrap up.
Yeah, sure. Yeah, no, that's fine.
Okay.
Yeah.
So I'll just give you like 2 other things that you might want to do once you have the posterior, and these are often how we might summarize the information. Okay, so given the posterior, so suppose we finished this process and we have distribution theta given y. Okay, so we might do 2 things. So these are two common things we might do with this probability distribution. We might want to calculate its mean. Okay, so the average value of theta given now that we have seen the data. Okay, so we might calculate expectation. Okay, so I'll just write it like this. So in other words, what is the average value of theta given data? And so what we do then is we would simply so we simply use the rule of how to calculate expectation. Okay, so in other words, we integrate over, okay, so in general, from minus infinity to infinity. So now we calculate this expectation now with respect to the posterior. So it's p of theta given y. Okay, so that's with respect to that's where the posterior is used. Okay, in calculating expectation of theta, so multiply by theta, and then d theta, right? So that would be it. So it's the usual rule of how you would calculate expectation, except now we call this a posterior mean because it's using the posterior distribution to calculate this interval. Okay, so that's quite useful because if you were to say, okay, summarize what you know about theta now that you've seen, let's say, two tails, right? So you could say, I think on average now, I believe theta would have this value. That's the posterior mean. So that's one typical way to summarize information. The other way is, so if I want to give a single number, you could do this, or if you want to give an interval, okay, so in statistics, often we don't just give point estimates, we also give intervals, and so because this is a probability distribution, we can also calculate posterior credible intervals. Okay, so you can say, what's the probability, now that I've seen the data, that theta lies between, let's say, two values. Okay, so let's say, what's the probability that theta now lies between A and B? Okay, so you can give some bounds on theta. Okay, so that's similar but not the same concept as confidence interval, but it's the Bayesian way of representing a confidence interval. But these are actually probabilities. Okay, so that's why we call them credible intervals. So what's the probability that you see theta lying between two values? You can calculate that again, just using the rules of probability. So integrate posterior from A to B. Okay, so you can then just use like very basic calculations to get. So these are two very useful ways to summarize what we now know about the parameter after seeing the data. Okay, so I think that should be good for today's introduction. Okay, any questions before I turn it over to some applications?
Any question, maybe also from the reading, like probably something came up that you guys have questions about? Don't be shy.
Yeah, don't be shy. Speak up.
That was a good time to ask questions. Yeah. Okay, yeah, I asked a question. So in part of the I think 1.2 on the 3 it talks about likelihood odd ratio. Is that a useful concept?
Yeah. So I actually have it in my notes. I didn't get to it today. There's also one other useful concept, which is I'll talk about yours first. So there's odds, right? So often in Bayesian statistics, so this might actually be come up in our later application in this project is let's say you have like two models, right? And that's the most general case, right? So you can say, well, what's which model is more likely given the data, right? So one way to do that is to take the ratio of the two of the posterior probabilities of the model. So probability of model 1 given the data, and then divide that by probability of model 2 given the data. Okay, so that's where it will come up, and the relationship is the odds. So in other words, the posterior odds of the models is related to the prior odds times what's called the likelihood ratio. Okay, and so the likelihood ratio is the likelihood of the data that you would see the data you've seen given the first model divided by the second model. Okay, so that's actually how you update your belief about like which model is better. Okay, so that's sort of like the higher level Bayesian updating, which is I've been talking about today. So that's where odds will come into play. So that is a very useful concept. So the term that we can look at later is called Bayes factor. Okay, so that's related to this idea of updating the odds after seeing data. And we use the Bayes. use the base factor and the size of the base factor to assess from a quantitative point of view whether how much better is model 1 compared to model 2. Okay, so this might in fact be quite useful later.
So I have a question about 1.3.
Mm-hmm.
We have the notation like PR, probability of an event.
Yes.
So can you explain further?
Oh, let me. Which page are you on?
I think it's talking about page 6. You know, the book uses PR instead of P of, like the way you. I think it's just a notation. Like it says probability in the notation of page 6 in the middle of the page.
Middle of the page. Yeah. So the book just uses small. Oh, PR. Okay. Yeah. Yeah, I see. So so instead of so I use small p for distributions, and I use big P for probabilities. So that's how I distinguish it. So here's big P because this is an actual probability, right? And this is an actual probability. This is, I guess you can't really tell on the board. So yeah, but anyway, yeah, that's just I guess that's just a convention thing. Yeah.
Okay.
Mm-hmm. All right, anything else before I pass it on to one of you?
Yeah, well, for the interest of time, if no questions for now, if there is, Samuel, are you okay if people post questions on Slack?
Yeah, for sure.
Yeah,
I'll take a look. Yeah.
Okay, so maybe we can move on. Who was supposed to do the first example? I think